Rest of the workflow, we are going over different algorithms. So here I tried a decision tree classifier, and in all these cases, very interesting to note would be not just the train and test accuracy, but you can look out for the false negatives. For example, you can look out for this one. So very clearly with a logistic model, I was getting 24 false negatives, and you can see that gradually as we try different algorithms with decision tree, I'm getting only 20 false negatives. You can see incrementally we got a better model. This is what we are trying to improve right now. So now all of a sudden, it's not just the overall accuracy that matters, but what is far, far more important is the false negative. Because remember, maybe let's say this could be an agreement you have with the customer that your test data set, even if there is a single false negative, we cannot allow, because even a single false negative can be very deadly. Because our classification model, we cannot allow to miss anybody who has diabetes. So it has to be that accurate. Okay, so sometimes machine learning model testing is very, very important, because that is how you go back to your customers and you show the results to your customers. There'll be a customer side testing that they will do. They will take some sample data from their end and they will give you a confusion matrix report. So this confusion matrix is very, very important. It's a very important part of any research papers or model testing. So and you will often talk to your customers in these terms. You will say, okay, this is the number of FNs I'm getting. This is the number of FPs I'm getting. Okay, like that. Rest of the parts are very similar. I think there's not much to talk about. This is the gradient boosting classifier I'm using, and you can see this is the hyperparameter and estimators that I'm using, and very clearly gradient boosting is a better model. So my not only is my accuracy numbers up, but also my false negatives are much lower. Okay, so see the incremental improvement that we make. Okay, and another very interesting learning from this exercise would be that no matter what you try, beyond the point you cannot get very good results. And that's just the nature of my data, something that you have to accept. Okay, there's nothing we can do about it. No matter what we try, beyond the point I cannot get very good results, because my data itself was so bad. If you go back to your original data, the data was very bad. If you remember, the classes were highly overlapping. Although we saw that there were some features which were good, the plasma features seemed to be kind of good. But even then, I mean, how do we define good? Like, it's not a very good separation, right? I think you can relate to it. The separation isn't that good. I mean, it's an okay kind of separation. It's not a very good separation, right? That is one thing that you have to keep in mind. We are not seeing a very good separation between the classes. So whatever you're seeing on the screen right now, we are not able to see a very good separation between the classes. So the separation is kind of okay, but we aren't seeing a very good separation between the classes. That's important to keep in mind. Okay, so you can see this is the blue class, this is the orange class, and I mean the other features. You have pressure, you have skin thickness, you have test, you have body mass index. So all these other features that you see, these other features, if you take a look at it, the separation is not that good between the classes. So we are not able to see a very good a separation between the classes for these other features. That's an important thing to keep in mind. So that is the reason, and that is the primary reason why. If you when you're building the models, you're getting such a even something like a gradient boosting model, you're only getting up to an 81% accuracy. So despite you might be wondering that such a powerful algorithm, why am I getting only 81%? Why not more? Why are the false negatives 18? Why can't it be close to zero? And it's difficult. No matter what you do, beyond the point, if your data is bad, the models will be bad. There is nothing you can do about it. That's why in data science, the data is such an important part. You need to have the right set of features. The inherent data has to be good. Only then the algorithms can model it. Okay. If you just have a powerful algorithm, nothing will work. If your data has to be right. That's why we put so much emphasis on data pre-processing, feature engineering. You know, so model building comes much later generally. Okay. So just one small pointer I wanted to mention. Something I mentioned at the very end. This is a process of hyperparameter tuning. If you remember, I told you that all the different algorithms that we have. So maybe decision tree is slightly different. We have talked about an estimator. So let me use this with respect to tune the hyperparameters. It will try to generate the code the same way. You'll be surprised, like how it does it for the gradient boosting classifier using grid search CV, and it'll actually try to tune the hyperparameters of the gradient boosting classifier using this thing. I think it's really made it too complex anyways. So what we can do is we can actually go and tune the hyperparameters of any algorithm, okay, using something called grid search CV. If you remember, I told you that hyperparameters are these tuning knobs. So decision tree is a kind of an algorithm. It has something called depth. I will talk a little bit more about decision trees very briefly in tomorrow's session. I will recap that idea once again for you, what exactly it is. Okay. So right now we're just kind of doing this at a very application level, at a very hands-on level. But what is it? We will have a small discussion on that. I will talk about that also very briefly. I'll come to that. Okay. So decision tree has a hyperparameter called maximum depth. Random forest and gradient boosting, they have hyperparameters called n estimator. So different algorithms have different hyperparameters or different knobs that you can tune. Okay, you can go to any algorithm and you can tune the different knobs in the algorithm. You can tune the knobs in different ways. Okay, so you can tune the knobs of the algorithm in different ways. Excuse me. That's the whole idea, right? That's the whole idea here in this case. So the concept is somewhat like you use something called grid search CV, and you use uh, the maximum depth here. This is the decision tree hyperparameter, and you set a range 2 to 10. And all that you're doing is you're finding out that so it's like you're taking different values of maximum depth, and you're finding out what is the best maximum depth. So that is what is basically happening behind the scenes. So I think this is not defined right now. So we can go and if I define the decision tree classifier from sklearn dot tree, import decision tree classifier. If I just do that, so the model will actually tune the hyperparameter. So grid search CV is also not defined. So let me just go and from sklearn dot model selection. Okay, import grid search CV. I think some of the code went away most likely. That's why it's giving this issue. So see, whenever we have a tick mark basically means that the cell is successfully executed because I did not execute the remaining cells. That's the reason why we're getting this error. So let me run this, no problem. Let me run this. So I'm going to just quickly run this code. So now X train, Y train, X test, Y test is set. This is all that we wanted to do. Let me just run this code. And now we can go and we can scroll all the way down. And now I can use this. So what it will do behind the scenes is it will go through the different hyperparameter values. Okay, we can use anything. We can use decision tree. We can use gradient boosting. Okay, if you're more comfortable with gradient boosting, because that's what we have done in the class, right? So we have used something called gradient boosting. So let me change it back to gradient boosting. So and gradient boosting has a hyperparameter which is n estimators, right? Excuse me. And we can take a range of 2 to 100 in increments of 10. So what it means is we're taking different values of n estimators. It could be 1, it could be 11, it could be 21 in increments of 10. This is a step. Okay, so this is the min value, this is the max value, and this is the step. Okay, it's like you're trying out different values of n estimators. You're trying out different values of n estimators. You're building different models, and you're seeing that for which model, for which n estimators value, we have the best accuracy. That is quite literally what it is doing behind the scenes. So if I just run the code, I think this is gradient boosting classifier. It will take a little bit more time behind the scenes. Let me call it gradient boosting classifier. And you can see very clearly, it has given me that the best one, okay, if I run the code, you will see the best one is actually n estimator 31. So this is the way how you will do this in the real world. You will take the training data, you will take the algorithm, and you will first decide what is the best algorithm, and then you will decide what is the best hyperparameter for that algorithm. And once you know that, okay, n estimator 31 is the best one, once you know n estimator 31 is the best one, now what you do? Now you build a full model. You build a full model on the whole data. Fingers crossed. I think Gemini should generate the code. Let's see. But if it doesn't, I'll write it for you on the whole data. Let's see. I think it should understand what I mean to say. But I think unfortunately it does not. Does not. I'll have to explicitly write it. Anyways, no problem. So we will use gradient boosting. Hopefully, if I give it a little bit of help, it will figure out. But these are some, these are obviously, it's not that machines will understand everything today, but it's a phase. So, and I think it should understand, but it still didn't actually. If you see, dot fit, X train, Y train, X train, Y train, and now this is the final model. So this is how I'm building the final model, and then I will calculate the accuracies and all that. I think by now it will, yeah. I mean, this part it's able to figure out, but the initial part it wasn't. So now I can calculate the train accuracy, test accuracy. This is the best model I got so far. Okay, so and remember, the cross-val scores are also important. I can get the cross-val scores. Hopefully, it should figure out. Yes, it does it. So yeah, so we can get the cross-validation scores. Okay, so get the average cross-val score. So what is the average cross-val score? Okay, see, I'm just typing average. I'm just starting to type average. It's figured out. It figured out what I wanted. So did a nice job, right? Yeah. So look at this. Yeah, decent. Let me remove the confusion matrix. It's not required. Yeah. So this is the end-to-end, right? So the important learning was how we tune hyperparameters. Okay. So first part, we take the data, we do the pre-processing, we identify good features, we try different algorithms, decision tree, random forest, gradient boosting, logistic. We try different algorithms that we have in the sklearn arsenal. Okay. And then what we do, we try to tune the hyperparameters for these different algorithms. So when we are doing a gradient boosting, we try to tune the hyperparameters for gradient boosting. In this case, we did that. We use grid search CV for doing that. So we try different n estimator values, n estimators 1, n estimators 2, 3, 4, 5, 6, 7, 8, 10, 100, 1000. We take different values of n estimators. And by taking different values of n estimators, you're trying to find out what is the best n estimators. And once you narrow down, once you get that n estimators 31 is the best, what we do? We build a full model using n estimators 31. Okay, all right. Be very careful when you're using generative AI, because if you're using Colab, I mean, it can be very embarrassing if you're sharing this code with somebody, like, I mean, I just wanted to let you know, whenever you generate code, know that you get this kind of thing called generated code, right? So just be aware of this, okay? So, so whenever you're using prompts to generate code, if you're using Colab's, Gemini features to generate code, you will get this thing, right? You see this thing? So this will not go away, okay? Just be aware of this thing. Yeah. So if you're generating code, be aware of this thing. And this is the concept that is not only applicable for classification, you even have this for regression. So the idea is very similar even for regression. Just wanted to let you know. So this idea is applicable even for regression. Even for regression, this idea is applicable. Okay, so please keep this at the back of your mind. You have this idea even applicable for regression. Okay. So what I want to do now is I wanted to share a similar data set with all of you. Very similar use case I will share with all of you. This is on classification, but I'm taking a slightly different use case now, a slightly different use case, but based on classification itself. But the reason I'm taking this data set is to show you that how you can build a, like, how on the same kind of thing we can build a better model. Okay, if the data is better, how you will get a much better quality model. Okay, but the core ideas are very similar. This is the cancer data set basically. It's a very real world data set uh, from the Wisconsin, you will see Wisconsin cancer data set is what we have here. So I've shared a PDF file that talks about how this data was collected, what kind of things happen behind the scenes, how we took the data. Okay. And then this is the actual data set. Okay. The Wisconsin breast cancer.csv. You have different features of the cancer cells. Okay. You can see that starting from column C, these are all the different features of the cancer cell, C, D, E, F, G, H, I, all the way. So we have actually analyzed every cancer cell under the electron microscope, and we have identified the different features of a cancer cell. So these are the different features of a cancer cell, the X as we call it. And based on this, we are trying to predict the diagnosis, the Y. So diagnosis can be B, benign. Benign means it's not, it's harmless. Or M is malignant. That means it's harmful, it's dangerous. So this is the classification that we are trying to do. So you can ignore the ID column. ID is an identity column. You can ignore that. But The objective here is we are looking at the different features of a cancer cell to predict its diagnosis status. It's either benign or malignant. Okay, the approach is very similar. I mean, we are solving it the same way. You can see that this is our data set, and I mean, so we have the features, we have the diagnosis, this is the Y, and we are solving the same way. And I wanted to share with you a couple of things. First thing, the pair plot. Very interesting. It's a huge pair plot, I know. It's a very, very big pair plot, you can see. If you take a look at it, one of the first things that will come to your mind is that we are seeing a much better separation between the classes, right? If you compare this with the PIMA diabetes one, the PIMA diabetes was overlapping. Okay, the classes were not that well separated. So the data was not good. But if you look at the cancer data set, the data is a very good quality data set. For example, if you look at the radius feature, we are seeing a very clear separation between the classes, isn't it? Look at this. Look at the kind of features we have here. If I just show you one other example, look at this feature. Look at this feature called points worst. Look at this. Look at how clear the separation is. And why is it important? Why am I talking about this? Because if you have a better quality data, this will give us upwards of a 90% accuracy straight away. And after that, if you further tune the parameters, use a better algorithm, you will get better results. But this is the important part. You look at a data set, you frame the problem, you look at the data, you look at the pair plot, you look at your feature importances, and at the first glance itself, you should know that, hey, I think I will get very good results here. I'll get very good results here. That's the idea. If you take a look at this here, these are very, very good quality features. In fact, if you look at the radius main feature, I was talking about the radius feature. I think it's logical because if the radius is more, the person is more prone to have malignant cancer, orange. The higher the radius value, the person is more prone to have malignant cancer. You're more prone to have the orange color. And if the radius is less, you're less prone to have the orange color. So radius is actually a very, very important feature, isn't it? Like if the cancer cell is bigger in size, it's more likely to be malignant, else it is more likely to be benign. So that's the inference we are able to make. So the cancer cell is actually like you can take a look at it here actually. So this is a good data set actually, right? So lots of features. There are features which are bad. Like if you see like somewhere here, these are poor quality features. There's no separation. So when I do the feature importance, these are the kind of features I should drop. This is what will contribute to the noise in my data. So there are 31 features we have overall. So out of these 30 odd features, 30 features we have. So out of these 30 features, maybe 5, 6 are very bad features. We should drop them. But the remaining features are good quality features. We should use them. That's the idea. That's the idea. Now, rest of it is very straightforward. We are going ahead and building the models. You can see this is the baseline logistic regression model I am using. This is something we already discussed. Nothing much to talk about. And with a straightforward logistic regression, I'm straight away getting 93% accuracy. And the reasons I talked about. The reasons I talked about already, because the data itself is very good. If you look at your data, you're able to very clearly visualize a very good separation of the classes. So the class separation itself is very nicely visualized here. That's why when you are using these algorithms, you're able to separate it out very accurately. Because remember, classification, you're ultimately trying to separate the classes. So we're getting a very good accuracy. And then we can use a pipeline, we can use other algorithms like decision trees. We're doing slightly better, 94%. False negatives are 0. This is very good, right? 0 false negatives. You can see that it's an excellent model we're getting right now. And then we can do grid search CV for hyperparameter tuning. So we talked about this. We can tune the maximum depth of the model. Okay, so all these are very, very similar to what we talked about. Okay, this is like seeing a validation curve for a random forest model. Remember, the hyperparameter value for a random forest is n estimators. Okay, this is the tuning knob that we are trying to tune, right? And you can clearly see that when the n estimators value is less, the model seems to be very underfit. The training and validation scores are very low. And when the n estimators value increases, we get to an overfitting zone. Okay, so lower the n estimators, we can see the model is underfitting, and higher the n estimators, we can kind of say the model is kind of overfitting. That's the inference we can make out of it. Okay.